Hey guys, today we're going to take a look at our product properties of exponents, our Unit 6, Day 3. Our essential question today is how do I use product properties to simplify expressions? Let's start by talking about simplifying. Last week when we looked at our first couple lessons, we were reminded that simplifying means that you can't have any exponents of 0, 1, or even negative exponents in your answer. Now today when we simplify, we're going to add to that and say that the same base can't appear more than once within a problem. So here are some examples. The one with the green circle would be okay because we have three different bases here, x, y, and z, and all three of the bases have positive exponents. In our other example, kind of crossed out here with the red circle, we have m, n, and another m. So notice how we have two different bases, two different powers with the same base of m in that problem. So that is not simplified. Now, we will learn throughout this week how to simplify something like that, but we're going to start with product properties today. Our first product property is called the product of powers, which says you can multiply powers with the same base by adding their exponents. So what we have here is we have a power, a to the m, times a to the n. Keep in mind the word product means that you're multiplying, or the solution to a multiplication problem. So what we have here is we have a product of two different powers. That's why this is called product of powers. And what we're showing here is that if you want to multiply powers with the same base, all we have to do is add the exponents together. Now that might seem weird, like you might be tempted to actually want to multiply the exponents together, but you can't and you don't. You actually add them together. So why does this work? Let's take a look at the example below to show why this works. If we have c squared times c to the fifth power, and I want to write this in expanded form. Expanded form means to show the repeated multiplication. So c squared is just c times c. Okay. Now, if we also want to expand c to the fifth power, we'd have to write that out as c times c times c times c times c. I'm trying to color code there so you can see the difference between the two powers when it's written in exponential form, but also when it's written in this expanded form. And when we have it in expanded form, we see it's just a bunch of c's being multiplied together. And if we wanted to write our solution, our simplified form, all we have to do is figure out how many c's were being multiplied together. So we just count them. 1, 2, 3, 4, 5, 6, 7. C to the seventh power. Now, we don't like having to count those one at a time. Instead, look at the relationship between the exponents. We had two of the factors in the first power and 5 of the factors in the second power. So altogether, there were 7 c's that we multiplied together. Let's apply this to some examples. Example number 1. We have d to the fifth power times d to the 12th power. Well, our property says that we can just add together the two exponents, so 5 plus 12, and we should get d to the 17th power. If you want, you could actually write all of those out and say, well, d to the fifth power would look like this. And then we have d to the 12th power. Just barely ran out of the room. And then our solution would be when we write that expression with one power, one exponent, and count them up. There are 17 d's that are being multiplied together there. And I know that there's 17 without counting them because I had 5 in the first group and 12 in the second group, and 5 plus 12 is 17. All right, looking at our second example, on this one, their exponents are quite large. I don't want to write out all of those different p's on my page here because that would take a lot of time, and I don't need to do that. We've seen the pattern. As long as I'm multiplying the same base or the same factor over and over again, all I have to do is add together the exponents to get my simplified form. So 31 plus 14 is 45. So it's p to the 45th power. All right, let's look at our second product property. This one is called power of a product, which might be like, wait a minute. We just talked about this. Now it's a little bit different. The last one was product of powers. This is power of a product. So let's talk about what that means. A power of a product means that you're raising an exponent to something that shows multiplication. So as an example here, we have two things being multiplied, two factors, a times b, and because they're grouped together in the grouping symbols and then raised to the power, that's power of a product. Now, power of a product basically says that you can write the expression with each factor in the product having the same power. For example, instead of a times b all raised to the power of m, we can write it and say that, well, then a is raised to the m power and b is raised to the m power. It's almost like distributing the m, distributing the exponent to everything inside the parentheses. So how does this work? We have an example here, 3h in parentheses grouped together, raised to the second power. So one way to look at this is to say, well, 3h raised to the second power means that I'm multiplying 3h times 3h. Well, we know that each one of those 3h portions is really 3 times h. So 3 times h times 3 times h. So we could actually take this and rearrange using the commutative property and say, well, it's 3 times h times h, which, when we simplify that, 3 times 3 is 9, and h times h is h squared. It becomes 9h squared. Now, using the property, if we were to actually show our work doing that, we distribute the exponent. So we say it was 3 times h squared, and each one gets squared. And we would result in 9h squared that way as well. So when in doubt, you can always write it out in expanded form and then kind of group together your like factors when you simplify your answer, or these properties allow us to get there a little bit faster. All right, example number 3, we have x times y is grouped together and raised to the 7th power. So we're going to go ahead and apply our property that we distribute the exponent and we get x to the 7th power times y to the 7th power. And we have two different bases there raised to an exponent. In number 4, we have 5w grouped together raised to the negative 3rd power. So if we want to go ahead and ungroup those, 5 times w, and in each case it gets raised to the negative 3rd power. That's using the property, but now the issue is that's not simplified. Last week we talked about negative exponents aren't simplified. What we do is we flip the positive. We're going to end up making this 5 to the 3rd power in the denominator and w to the 3rd power in the denominator. Because remember, we have to move everything down. If that's a negative exponent, we move it down to the denominator, and then what's left over up top is just that invisible 1. So 1 over 5 to the 3rd power times w to the 3rd power. Now the only other thing I would say is to go ahead and simplify 5 to the 3rd power. So 5 times 5 times 5, which is 125. So we're going to write this as 1 over 125 times w cubed. All right, a few more where we kind of mix things up a little bit. In number 5, we have m times n to the negative 4th power times m to the 4th power. And in this case, we notice that the product of powers only applies to the parts I'm circling because those are the only two powers that have the same base. In each case, the base is m. So I have to remember that this m at the beginning is m to the 1st power. Okay, so m to the 1st power times m to the 4th power. Let's see, my product of powers said, oh, that's right, I have to add exponents together, because if I were to expand this and write it out, I would have an m multiplied by itself 5 times. Now, I'm just going to bring along my n to the negative 4th power for now. And now I'm going to deal with the fact that it's not simplified because I have a negative exponent. So my next step would be to simplify the negative power. So I flip the positive and I leave m to the 5th power in the numerator, but I move the n to the denominator and make the exponent positive. My final answer would be m to the 5th power over n to the 4th power. All right, last one is number 6. You can see what we have there. We've got some grouping symbols. We've got some negative exponents. We also have two different types of bases here. We've got x's and y's appearing. So let's see how this one will play out. X times y to the 3rd power times x to the negative 4th power. Well, let's start by simplifying where the parentheses are. We have x times y, and that was each raised to the 3rd power. Okay, so that's just simplifying this portion of it. And then we still have x to the negative 4th power as part of it. I just want to bring that down. All right, so now I look at that and I see that I have 2 powers with x. So I want to combine those together using one of my properties. And because it's a multiplication property there, x to the 3rd power times x to the negative 4th power, I remember that I'm supposed to add the exponents together. So x to the 3 plus negative 4th power. So if it's helpful, don't forget you can always double check using your calculator. 3 plus, and I always like to use parentheses around the negative numbers just to be safe. I can never trust my calculator otherwise. And when you add together those two exponents, 3 plus negative 4, we do get a power of negative 1 for the x. So this is going to become x to the negative 1, and then we bring down the y cubed. And we're close. We've got the x's together, but now we still see that there's a negative exponent, so it can't be our final answer yet. We want to go ahead and flip the positive. So we have to think about, all right, if this was a fraction and we wanted to flip the positive, I have to take this negative exponent, move it down, and it's going to become, let's see, y to the 3rd power stays in the numerator, and then my x to the 1st power is going to move to the denominator. So it's just y cubed over x.